7.
Yeah, location 7.
Hi, my name is Sakrit. I am a SM for CSM EE16A, and today we're going to be doing a walkthrough of worksheet 7. Alright, so let's get started with question 1. It's a bird, it's a plane, no, it's superposition. Right, so basically we have this circuit, and we want to try to solve for a certain voltage, Vx, using nodal analysis. And so what I like to do to get started with circuit problems is just go ahead and write out what I know and write out the signs on the resistors so that we can stay consistent with passive sign convention. So I'm just going to go ahead and label these. And again, remember, it doesn't really matter the orientation as long as we say consistent throughout the question and say consistent with our passive sign convention. So I'm going to label it like this. And another thing to notice is that over here we've grounded this node, and so we know that the voltage here is 0 volts, and so we know that the voltage at this point is V1. And the reason we know that is because just what a voltage source promises us is that the potential across the source is equal to the value of the source. And so since this is V1, the voltage here will be 0 plus V1, which is V1. Also remember, the way I've labeled these resistors is keeping consistent with passive sign convention of the currents as they've been labeled here. Okay, so now we can go ahead and get started with some KCL at the node of interest. And so just the way the currents have been defined and doing KCL at this node, we get the relationship that I1, which is the current entering the node, is equal to I2 plus I3, which are the currents exiting the node. And now the idea is that we want to take I2 and I3 and express them in terms of known quantities. So just looking here, looking at I2, we can go ahead and solve for I2 using Ohm's law. And so what we see here, just refresher on Ohm's law, is that delta V is equal to IR. So the change across a resistor is equal, that's not the right thing. The voltage change across a resistor is equal to the product of the resistance and the current flowing through the resistor. And so the voltage at this point is Vx, which is the quantity we're searching for, and the voltage at this point is V1, which we found earlier. And so we see that Vx minus V1 is equal to I2 times R1. And we can just rewrite this in terms of I2 by dividing by R1. Okay, so that takes care of the left branch. Now we could go ahead and look at the right branch. So again, we can look at what this voltage source, in this case a dependent voltage source, tells us is happening. And remember, what a voltage source tells us is that the potential across the source is equal to the value of the source. And so we know that the potential here, which is Vx, minus the potential here, which is Vb, is equal to the value of the source, which is 2I2. Furthermore, we can express Vb again using Ohm's law, which is going to be Vb minus 0, because the value here is 0 because this node is grounded, is equal to R3 times the current flowing through the resistor. And here the current flowing through this resistor is actually I3. And the reason that is because currents, the current is going to be the same on the same branch. And because all these elements are in series, we can say that they're on the same branch. And so the current flowing here is I3 is going to be the same as the current flowing through R3. So we get this relationship. Now we can just plug VB, the expression for VB we got here above, and then we can, so we can take this quantity and express it just in terms of I3, which is going to be Vx minus 2I2 over R3. Okay, so Now, taking what we've solved, we can plug everything back into our original KCL equation to get I1, which is equal to I2, which is Vx minus V1 R1, plus I3, which is Vx minus 2 I2 over R3. And then I can just substitute in I2 for the same quantity that we found here. Okay, so now we can just go ahead, plug in all our known quantities, and we should be able to solve for Vx. So let me just write this in. You see that 6 is equal to Vx minus 7 over 10 plus Vx minus 2 times Vx minus 7 over 10 all over R3, which is 2. And then from here, it's just, we have one equation with one unknown, and so we can just rewrite this in terms of Vx to solve. Then I'm going to multiply both sides by 2. Let's just rewrite this as that. And so we see actually that we have Vx minus 7 over 5 minus Vx minus 7 over 5. So these two can cancel, and we get our final answer as Vx is equal to 12. Cool. All right, so now that we've gone ahead and solved this problem using nodal analysis, we want to try to solve the exact same problem, but now using superposition. So I'm going to go ahead and take this exact circuit, and the way we do superposition is we null out each independent source at a time and solve for the same quantity. And then at the end, the idea is that we can take each answer from each, stage and add them all up together, and we should get the correct answer. And so I'm going to start off by nulling I1 out. And so let me go ahead and redraw this circuit with that. All right, so now redrawn this circuit with the current source nulled. And what happens when we null a current source is that basically we set its value equal to 0. And in the case of a current source, what that means is that no current should flow on that branch. And so we can redraw that as we've done here as an open circuit. Okay, so now we're going to proceed like we did earlier with a similar sort of setup. So let's start by doing, again, KCL at this node where Vx lives. And we see that I2 plus I3 is equal to 0. Because there are two currents, I2 and I3, leaving the node and nothing entering the node. Okay, so again, we have some I2 and I3 that we don't know what they are, and so we want to try to rewrite it in terms of other things. And again, we will be employing similar tactics such as Ohm's law and more KCL. So just to reiterate, we have this node grounded, so this is still 0 volts. And again, how voltage sources work is that this will be V1. Okay, so what we can do is now say do Ohm's law on R1 and say Vx, which is the potential at the top of the node, minus V1, which is at the bottom of the resistor, over R1 is equal to I2. Cool. And that expresses I2 in terms of known quantities, except for Vx, which is what we want to solve for. Now we can go ahead and tackle the right side of the circuit. So we see that, again, very similar to what we did earlier, using our knowledge of how voltage sources work, we can say Vx minus Vb is equal to 2I2. And then we can express Vb using Ohm's law with this resistor here. Again, reiterating that the current going through R3 is I3, and it's because it's all on the same branch and in series, and so the current will be the same. So we can, now taking this, substitute it back in to see that Vx minus I3R3 is equal to 2I2, which means that I3 is equal to Vx minus 2I2 over R3. So now we can take this value for I3 and this value right here for I2 and plug it back into our original KCL equation to see that Vx minus V1 over R1 plus Vx minus 2, and again I'm just going to substitute in this value for I2 from what we found, Vx minus V1 over R1 all over R3 is equal to 0. Alrighty, so now we can substitute in our known quantities to get Vx minus 7 over 10 plus Vx minus 2 times Vx minus 7 over 10 all over 2 is equal to 0. And we can do further simplifications to find that Vx has to equal 0 in this case. Alright, so we have done the first step of the superposition, which is nulling out the current source and keeping our voltage source. And now what we're going to do is the other way around, where we null out our voltage source and keep our current source and then solve for Vx. And the way we null out a voltage source, just to remind you, is by replacing it with a wire. And the reason that is because by nulling a voltage source, what we're saying is that the value of that voltage source is equal to 0. And what that means is the potential across the voltage source, like the potential change, is 0, which is the same thing as a wire. And so, as you see here, I've taken out that voltage source and replaced it with a wire and put our current source back in. And now again, with this setup, we can just jump right in using KCL at that node Vx. And we actually get the exact same relationship between currents as we did when we did our nodal analysis, which is that I1 is equal to I2 plus I3. And again, we want to express these currents in terms of other known things using Ohm's law. So I2 can be written as Vx minus 0 over R1, because now the potential here is Vx, and the potential here is, instead of V1, it's now 0 because this node is all grounded. And that's equal to I2. All right, so that takes care of the left branch, and now we can look at the right branch again. And this right branch is actually the exact same as it was in previous parts of the question. So I'm just going to go ahead and rewrite basically using the exact same methods as we did earlier, but just to save time, rewrite these equations quickly. And then VB is equal to I3R3. And so I3 is equal to Vx minus 2I2 over R3. Okay. Now, taking this value for I3 that we have and this value of I2, we can plug everything back in to our KCL equation to get this. And then we can start plugging in our known values. Or actually, rather before that, let me just express I2 up here in terms of what we had found it to be. And now we can start plugging it in with the values we know. Like such. And then all I'm going to do is multiply both sides by 2. And then you'll see we have this, in which, again, these two quantities here cancel out, and we get Vx is equal to 12. And so, in this case, it turns out that this is our final answer, but I want you to remember that the way we do superposition is that at the end of the day, your Vx, like final, is equal to the first Vx that you found plus the second Vx that you found, which in this case was 0 for the first case and 12 in this case, which is just 12. But it's important to remember that our final answer is the combination of the answers we got in the various parts of superposition. And as we see here, it doesn't really matter how we approach solving the circuit, whether it's nodal analysis or superposition. At the end of the day, we will end up with the same answer. It's just a matter of how you want to get there, which is it's good to know the various paths because some might be easier than others.